Hello, I'm Otri Roy, a BS Data Science and Artificial Intelligence student here at IIT Guwahati. In this video, I will explain my internship project on cyclic vectors in differential module, a machine learning approach, and how I combine symbolic mathematics with machine learning to automate deep algebraic property. At the first glance, cyclic vectors looked to me as a part of abstract mathematics, but the core question was much more deeper. My core question was, can I teach a machine learning model to understand and automate and predict an algebraic property that is traditionally verified symbolically? The reason for that, traditionally verification symbolically was computationally expensive in nature. So we have heard about differential equations in mathematics and physics. So these differential equations can be represented in matrix form, especially in higher dimensions. Now a cyclic vector is a vector whose derivative repeatedly regenerate the entire vector space. So there is a repeated regeneration of the derivative to get the entire vector space. So if a vector can do that, it's a cyclic vector. But the issue comes here, repeated regeneration of the differentiation, that is the higher order derivatives. So we know the issue with the higher derivative, that again you have to compute this, and that is very expensive symbolically. So, and why cyclic vector? The question can come. Because it reduces a matrix value differential system into a single scalar system. In simple words, it can reduce an n value differential system to a single value differential system. That is a huge jump. And that helps to simplify analysis, computation, and it also serves as a crucial role in differential Galois theory, p-acidic differential equations, linear algebra, and abstract geometry. However, verification is computationally expensive, as I had discussed now. It requires symbolic differentiation, determinant calculation, rank calculation, and others, which become increasingly complex as we move up the size. Because, for example, if I take a five dimension, so a five value matrix formula to a single value, so that means five order derivative. That is quite a computationally expensive task to do. So I had this problem. This was the central idea of the problem, of my research problem, and to solve this, I had built a symbolic pipeline to verify the cyclicities in the CADS algorithm. Now, why I'm using the CADS algorithm? I had used Nicholas Carr's paper as a central and the baseline paper for my research study, and so I will be using the CADS algorithm, CADS matrix, because that is his way of defining the model, and that has been verified by a number of scientists, and that I have also verified symbolically, and it is true. So explore, and my second task was to explore a machine learning paradigm that can predict cyclicity directly from the algebraic features. In other words, can machine learning approximate a deep algebraic criterion without losing the mathematical correctness? So that can be summed up in a very short way. So when I implemented the CADS vector symbolically, so we all know that we need an input. So the input was the connection matrix, a basis of vector space, and a shift parameter. I constructed a candidate cyclic vector using CADS universal formula given by him in his paper, which I've also illustrated in my research report. Then I built a CADS matrix consisting of a vector, its derivatives, and higher order differential derivatives. So if CADS matrix is invertible, then the module is cyclic. So that can be said by him with the help of Darcy topology, and which has been also be illustrated by him in the appendix section as well. That if the CADS matrix is invertible at one point, also it is cyclic everywhere. So I had used the Streamlit package, SumPy, and Python, and automated symbolic differentiation, determinant computation, rank evaluation. That gave me an exact symbolic verification of pipeline. Using the pipeline, I generated a 10,000 differential system, and each label as cyclic or non-cyclic varied upon, and for checking the dataset, I checked with the help of the symbolic differentiation, and I found that it was more or less in the correct zone. The dataset served as mathematical correct ground truth for the testing and the training. Now comes the key innovation, the methodology. Symbolic verification is exact but slow. Machine learning is fast but approximate. So my question was, can we represent algebraic structure as numerical features and let a model learn cyclicity? So instead of feeding the raw symbolic expressions, I fed algebraic features such as trace, determinant, rank of connection matrix, eigenvalue statistics, norm and rank of basis parameters, shift and evaluation parameters. I then use a random forest, the supervised machine learning paradigm, that is a random forest classifier, because I was training on algebraic features, and random forest models nonlinear interactions between the algebraic features. So I went with the random forest. The results. Now for the results, I had an accuracy of 97.05%, a AUC score of 0.9922%, and a very low false positive and false negative. It is to be noted that the misclassifications happened, but near the degenerate classes, where even symbolic rank computation becomes sensitive in nature. This confirms model approximating the true algebraic boundary and is not deviating from the correct truth. So the project contributes at 3 levels. First is demonstrate algebraic property like cyclicity has a statistical structure. Number 2, hybrid pipeline, symbolic verification for correctness, and a machine learning for speed. This opens possibilities for higher dimensional differential system to be included in computational machine learning view as well. So the future work can be building an interpretable machine learning model that reveals explicit condition and incorporating norm-based features inspired by Andrea Pulita in her paper of small connections are cyclic as well. To conclude, this project shows that machine learning is not just a tool for data, it can interact with deep mathematical structures, especially algebraic features, by combining symbolic computation and machine learning. We can make abstract algebra computationally accessible, scalable, and intelligent.